So we have been talking about the four important distributions: the normal, the chi-square, the t, and the f distributions. We also mentioned that you can always calculate probabilities of getting a random number in a certain interval from these distributions. But typically, a much more common problem is the inverse problem. That is, I know the probability, for example, of the right-hand tail, and I want to find the value such that the probability of getting a number greater than this value is equal to the given probability, which might be, for example, 5%. So let's develop some notation for this particular problem of finding these cutoff points. These cutoff points will actually be called critical values. So let's start with the most important one, the normal distribution. Critical values from the standard normal distribution. So now we are dealing with, try that again, we're dealing with a probability density function that looks something like this, centered around 0. And the probability of the right-hand tail is given. So the probability of this right-hand tail is some given number alpha. The most common value for alpha in econometrics is alpha equal to 5%. Sorry, the most common value for alpha is alpha equal to 2.5%, because I've just drawn one tail here. If I have two tails, then the combined area of the tails would be 5%. But with just one tail, it would be 2.5%. So this number here, this cutoff point, which is the number such that to the right of it we have alpha percent, that's called a critical value. And we simply denote this value with small z alpha, simply because it depends on alpha. We can see that if I decrease alpha, if I make the tail smaller, then I have to move this z alpha to the right. So a smaller alpha must lead to a higher z alpha. The technical definition of this z alpha is this. We want the probability of our standard normal random variable. The probability that this is greater than z alpha should be exactly alpha. That is the implicit definition of z alpha. And the name we give for z alpha is the following. It's called the critical value for the standard normal with a level of significance equal to alpha. So this guy is called the level of significance. So let's summarize this. If z follows a standard normal distribution, then for any alpha between 0 and 1, we define the critical value z alpha according to this formula. Probability that z is greater than z alpha should be alpha. And z alpha is called a critical value for the standard normal with level of significance alpha. There is one alpha that you should memorize, there's one z alpha you should memorize, and that's the following. If this one is precisely 0.025, then z alpha is precisely 1.96, meaning that there is a 95% probability of getting a random number between plus minus 196 from this standard normal distribution. If you want to memorize one more, then perhaps this one is also pretty good. If we do 5% instead. So if I do 5%, then this z 0.05 is 1.64. So a 90% probability of getting a random number between plus minus 164. You can find the critical values using Excel by just doing norm dot the standard normal and the inverse. There's no right hand tail here, so we have to do 1 minus the alpha to get the z value and copy this down. So for example, we have 1.96 there and 164 here. This is probably the third most common critical value. And like we mentioned, and as you can see in this table, as alpha increases, the critical value will decrease. So there's this inverse relationship between z alpha and alpha. Z alpha depends negatively on alpha. Moving on to the t distribution, we do pretty much exactly the same thing. Now I have a random variable t that follows a t distribution with k degrees of freedom, and for any alpha between 0 and 1, alpha again being the size of the right hand tail, then we define t alpha just like z alpha, but we have to tack on a k here because we have several different t distribution. So we get a different critical value depending on how many degrees of freedom applies to our t distribution. So we define it very similar to the z alpha, just like that. And the name we give to them is the critical values for the t distribution with k degrees of freedom and a level of significance alpha. So let's plot, for example, t alpha for, I don't know, k equal to 3. Then they look like this. We need the t, we need the inv, and Excel has a right hand tail. Sorry, we need the no, it doesn't have that for the inverse. So we can do the t inv, and then we can do the same thing, just 1 minus the probability a2 and 3 degrees of freedom, like that. Copy this down, and you should notice a couple of things. First of all, the critical values decrease as alpha increases, which is not surprising. If you increase alpha, you make the right hand tail thicker. That means that you have to move the critical value to the left, just like before. But if you compare the t values to the corresponding z values, you see that they are always bigger. And the reason is this thing we talked about for the t distribution. It has fatter tails than the standard normal distribution. So you have to go further to the right to have a tail with 5% of the area. But we also talked about this, remember, if I increase this degrees of freedom, then the difference between these two will be smaller and smaller, and eventually they will pretty much be the same numbers. For example, if I go to 30, there isn't much difference between them. So we have this, again, inverse relationship between T alpha K and alpha. And as we mentioned before, very easy to find the critical values from, let's say, Gretel's statistical table. Here's this point that the corresponding T critical value is always greater than the corresponding Z critical value for all alpha, and no matter what the value of K is. But the difference between them becomes smaller and smaller as K increases. So we have this T alpha K converges to Z alpha. They become almost the same as K increases. And we can confirm that from the Excel table as well. If I change this to, say, something big, 50, now let's do even larger, 100. And I change this to 100. Copy down, then there's a very small difference between these two, 0.02. Make it even bigger, let's say 1000. Then it's probably gone away completely. You won't be able to see it anymore. Yes, now the difference is in decimals further beyond the first two decimals. Well, actually, there's one where there is a noticeable difference. Actually, two. Chi-square, critical values from the chi-square distribution. Same idea, but they're absolutely not comparable to the t and the normal distribution, because the t and the normal are symmetric around zero. The chi-square distribution will always give you a random number that's positive. But the idea is still exactly the same. It's just that we have to draw the diagram something like this. We have a chi-square distribution, maybe something like that, skewed to the right. I set the right-hand tail equal to some given alpha, and then this is my critical value, and we denote that by chi-square alpha comma k. That's the critical value. So we have this. Y follows a chi-square distribution with k degrees of freedom. Alpha is a probability, the size of the right-hand tail. Then chi-square alpha k is defined just like for the other cases, the probability that we'll get a number bigger than this, and that should be precisely alpha. And the name, we call it same thing, just change the name of the distribution. So it's the critical value for the chi-square distribution with k degrees of freedom, and the level of significance is alpha, that is the probability of the tail. You can do this yourself by just printing some critical values and see how that changes with alpha. But just from the sort of picture, you can see that if you increase alpha, if you make the tail bigger, you have to move this dashed line to the left. So that will move the critical value to the left, that is, it will take it down. So you have exactly the same relationship, namely the higher the alpha, the smaller the critical value. Finally, the F distribution, same thing. I have a random variable that follows an F distribution with k and l degrees of freedom. I have a probability alpha. Then I define F alpha, k comma l, as this probability that I'm in the right-hand tail with probability alpha. And this is called the critical value for the F distribution with k and l degrees of freedom and level of significance alpha. Same relationship, the bigger the alpha, the smaller the critical value.